Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, I will help get you started with Class 21 on Analysis of Variance, ANOVA, and Pairwise comparisons. So we'll scroll down to Class 21. And this has its own Markdown file and data file. So we will start by downloading these to the appropriate directory. And my classwork directory is where these go. The RMD file and the DAT file. And we'll open up our studio. Open the Markdown file that we just downloaded. And then we will knit this file, and we will also set the working directory to the source file location. And what the heck, I will also, let's just wait. Alright, so here is the assignment. I'll open it in the browser and zoom in a bit. In this worksheet, we're going to be looking at a data set that I also look at in the lecture notes. Alright, so the concept, recall from the lecture notes, that the concept of analysis of variance, it's like a two-sample t-test, but generalized to more than two groups or two samples. So you could have 3 or 4 or 5 groups, and you're asking, are all the means equal? Or does at least one pair of the means differ? So that's where there's sort of two steps. First, you ask, are all the means equal? And if that's the null hypothesis and you fail to reject the null, so the data are consistent with that null hypothesis that all the means are equal, then you're done. All the means seem to be equal. But if you reject that hypothesis in favor of the alternative that at least one pair differs, then you have to go forward and say, well, which pairs actually differ? If I've got 4 groups, then there's 6 possible comparisons. If I've got 5 groups, there's 10 pairwise comparisons. Okay, so those are the sort of the two steps. First, test, are all the means equal? And if not, then which pairs actually do we have evidence for that they differ? All right, so this example comes from the Kaiser hospitals in Northern California, where we have data on 680 babies who were born to mothers for prenatal care, and some of those mothers, we actually have several variables on those mothers, but in this example we are going to look at 3 groups based on the mother's smoking history. And I believe the data set, in fact, we have a CSV file. We can open that CSV file. And there is a mother smoke column. And in that column, I think that this is the number of cigarettes that the mother smokes each day. Something like that. Okay. All right, and we're going to use that variable and partition it into a few groups. In particular, those 3 groups are going to be that the mother doesn't smoke or maybe has never smoked. I guess it would be enough to say that the mother currently does not smoke. Then there's the mother smokes less than 1 pack of cigarettes per day during pregnancy. And then the third group is that the mother smoked at least 1 pack. So a pack of cigarettes is 20 cigarettes. And so we're going to create this 3 level factor variable from the numeric variable. We have a null, well, let's define some variables here. So mu1 or mu I is the population mean for population mean birth weight. Okay, so we're interested in the birth weight of the children. The population mean birth weight for the children in group I, where I is 1, 2, and 3, these three groups here. And we wish to test whether all the means are equal, that is, the amount of smoking that the mother doesn't affect the birth weight of the child, versus, and I've really simplified the notation for the alternative hypothesis, not H naught, meaning not all the means are equal, which implies that at least one pair of means differ. So mu1 might differ from mu2, or mu1 might differ from mu3, or mu2 might differ from mu3. Those three pairs, or more than one of those combinations, right? They could all be different, or mu1 could be different from mu2 and mu3, etc. We're going to organize how we do those comparisons at the end of this assignment. Okay, so first we read in the data set, and we're going to create this smoke factor variable. So we library the tidyverse, read in that data file. It's got all those columns, but we're going to be dropping a whole bunch of these. Just so you can parse this a bit, anything that starts with a C underscore means the child. So the child's, I think this is like head circumference, their body length, and their birth weight. Gestation is their gestational period, which might be in weeks. And then M underscore is for maternal age, smoking, height, and pre-pregnancy weight. And then P underscore is for the father, padre, papa, for age, their education, smoking, and their height. Okay, so after we've read in that data set, we start with that data set, we mutate to create a new variable called smoke, and we're going to create 3 levels of a factor variable. When the mother's smoking equals 0, then we're going to label that, the tilde means then the smoke variable will equal the label 0 cigs. Okay? If the mother's smoke is greater than 0 and it is also less than 20, then you've smoked between 1 and 19 cigarettes. And if it's greater than or equal to 20, then it is 20 or more cigarettes. And after that variable is created, then I'm going to make smoking a factor variable. And notice that because of the way I've labeled this, 0, 1, 2, alphabetically, that is going to be the order of the factor variable, which is exactly what we want. We want the non-smoking group to be the baseline group, and the smokers to be offsets from the smoking groups. Finally, we're going to select only the birth weight and the smoke column. And if we summarize the data set that we end up with, here's the this is the birth weight column. The minimum birth weight is 3.3 pounds up to 11.4 pounds with a mean of about 7.5 pounds. And then smokers, we've got 380 non-smokers, 170 low or less than a pack smokers, and 130 pack or more smokers. All right, I've created a plot here, and there's a lot going on in this plot. Let's just take a look at the plot, and we can come back and look at the code if we want. I don't think there's anything really new in that code. Okay, there's the plot. Can I zoom in one level more? Yeah. So along the horizontal axis, we've got 0 cigarettes, 1 to 19, and 20 plus. And I've labeled it maternal smoking per day. The vertical axis, we have the child's birth weight. You can see that goes all the way down to that 3.3 up to whatever it was, 12.5. And I've got the 3 groups. I've got box plots in here. I've got a violin plot that has the curved line around it, sort of a smooth distribution. Basically, I'm putting the violin plot in there to see if I've got skewness. for example, in the 1 to 19 cigarettes groups, it looks like there's a bit of a longer tail for higher birth weights. You know, if you look at the slightly longer tail on the upper than on the lower. So that helps me see a little bit skewness a little better than the box plot does. I've got all the points plotted. I've got the red means with the confidence intervals. I also have this dashed line in the background. And that dashed line is the grand mean. And the reason I put that for my ANOVA plots is because that is consistent with the null hypothesis. If the null hypothesis is true, then the means for all three groups are equal, which means that these red diamonds should all be very close to that line. And visually, it appears that the mean birth weight for the zero cigarette group is higher than that of the smoking groups, and the smoking groups look to be about the same. That's my takeaway from this plot, and we will soon see if that bears itself out statistically when we do the hypothesis test. Up here I'll just sort of point out a couple pieces of code. We start with the data set, we assign smoking to the X variable, child's birth weight to the Y variable. I've got this horizontal line where the y-intercept equals the grand mean of the child's birth weight. That's that dashed line, right? Color black, line type dashed. That's that dashed line in the back. Then I plot a violin plot, I do a box plot, I plot the points, and I jitter the points. I jitter their width, but not their height, so that in the plot, points are allowed to wiggle left and right because that doesn't distort the data because it's within a category. And they keep their vertical position, their height position, so that they're still an accurate reflection of their actual child's birth weight. So that allows me to separate some of the points without distorting the values. We've got summaries, which are the means for each group, and looks like I just did shape 18 is the diamond that we see here, and I like the diamond, I've mentioned this before, because it gives you corners, and the corner, that left corner is the actual value of the mean, where it's a little harder to see where the actual middle is if you've got triangles or circles or squares. I also have a stat summary, which is a confidence interval. So mean CL confidence limits based on the normal distribution. And I'm plotting that with error bars. And so those are a little bit hard to see here, but you can see those horizontal lines above and below with a connecting line that goes up and down through the diamond. That's the confidence limits. And then I just label the plot. All right. I said I wasn't going to, but there, I've gone through all the code. All right, we're going to set up our hypothesis test. In words, the population mean birth weight is different between smoking groups. I've stated it in terms of the alternative hypothesis, that the birth weights are different. We don't know how they're going to be different, but that's sort of the interesting way of looking at this problem, that they're going to be different. In notation, just as what we saw before, all the means are equal versus at least one pair of means differ. I'm choosing a significance level of 0.05, so that is alpha. I'm using the AOV, analysis of variance function, to perform this hypothesis test. The y variable, the numeric variables on the left, tilde the grouping variables on the right. And that's my data set. I'm putting that result into fit_c. I think the word fit is like fitting a regression model, and the _c is for child's birth weight. All right, so we'll look at the summary. The summary is actually very short for an analysis of variance table. We have the we have two lines. We have the smoking, which is the categorical variable, and we have the residuals, or the error line. We have 2 degrees of freedom because we have 3 groups. So that's just always the way it is. Degrees of freedom is 1 fewer than the number of groups. We have a sum of squares. The mean square is the sum of squares divided by the degrees of freedom. That's true also for the residuals. And the F statistic is the mean square divided by the mean square from the model for smoking divided by the mean square error, or the mean square of the residuals. So 20 divided by 1 with these little fractions gives you about 18. And when you compare this F statistic to an F distribution with 2 degrees of freedom in the numerator and 677 in the denominator, you get a p-value, or a right tail probability, that's very, very small. 0.70 and then a 2. Right, so it's 2.6 times 10 to the negative 8th. And these stars are relative to these significance codes. 3 stars is a p-value that's somewhere between, or a p-value that's somewhere between 0 and 0.001, and it is. Okay, so this is a significant result. So you can see we haven't really done anything yet. I'm just setting you up to make some answers. Here's where you're going to write some answers. The F statistic for the ANOVA is 17.9. I'll bring this up here. That's good enough. The p-value is 2.6 times 10 to the 8th, negative 8th. State the conclusion in terms of the problem. Okay, so if you compare, so this is your time to think about this. If you want to pause the video and write a conclusion, you can do that and then come back and listen to what I'm going to say about it. What I'm going to say about it is I'm going to compare this p-value to the alpha level and use that comparison to decide between either the null hypothesis or the alternative. Now this p-value is less than alpha, therefore the data is not consistent with the null. We reject the null in favor of the alternative, that at least one pair of means differ. So that's what I would write down here. I would write, because the p-value is less than alpha, we reject the null in favor of the alternative. At least one pair of the smoking groups differ. Okay, and we can get a sense here of which pairs are actually going to differ. It seems like the first group, the 0 cigarettes groups, is going to differ from both of the smoking groups, but the smoking groups are not going to differ. That's what visually this looks like. So far, our conclusion is consistent with what we see in the plot. All right, next we are going to check the model assumptions of the test. And the 2 assumptions are that the residuals are normal and the populations have equal variances. And we're going to check normality both with a visual check and a hypothesis test. And I'll say that the visual check is the one that statisticians prefer. Second, populations of equal variances. This is a bit less critical typically for the hypothesis test, but we still want to make sure that they're at least pretty close. And we're going to check sort of casually based on the standard deviations of the 3 groups, but also we have some hypothesis tests that can help us make a decision about that as well. All right, so let's first check whether the residuals are normal. And when we fit the ANOVA function, we created this fit underscore C, and there's a bunch of stuff in that fit underscore C object. One of those things is residuals. Okay, so the residuals, as you'll recall from the lecture notes, are the differences between the mean of the group and any point. Okay, so for example, do I have a good example? How about, I don't know, one of these points up here is like 10 and a little bit. The mean is 7.5 and a little bit, right? So 10 and a little bit. These points right here would have a residual of about 2.5. They're 2.5 units higher than the red diamond. Okay, and if we went down 2.5 units to about here, these points would have residuals roughly negative 2.5 because they're 2.5 lower than the mean. Okay, the way you calculate the residuals are it's the observed value minus the mean. Okay. These points that are close to the mean are going to have small residuals, and the ones far away are going to have large residuals. Okay, so first thing we're doing is just seeing whether all the residuals are roughly normal, and that means that we're lumping all the residuals together in one distribution. So this mean, right, residual, take each of these means and sort of line them up and then squash all the data together. That's the worst explanation. Anyway, so over here, right, we talked about these points that have 2.5 residuals. All right, so this one, 2.5 is going to be right about here. And so these points here are about 2.5 from this diamond, but they're not lined up with these points up here that are 2.5 from their diamond. However, in terms of residuals, those are going to be in the same spot in the plot if you shift all the data so that the means line up. We're interested in the differences from the means. So if you do that and, and plot the residuals, then, so we're making a histogram, we're putting a density plot over there, we're also plotting a normal function based on the mean and the standard deviation of the residuals, and labeling the plot. Okay, so here is the distribution of the residuals. The blue line is the fit to the histogram, and the red curve is a perfect normal distribution. So what do you think? Do these residuals look normal? Heck yeah. These look really good. Now there's a couple unusual observations out here. These are children with very low birth weights, but there's just a couple of them. Overall, you know, over 600 observations, this looks really, really good. So I would summarize what I just commented on here, that basically the residuals are consistent with the normal distribution. So the model assumption for normal residuals appears to be met. Another way to look at this is with a QQ plot. This stands for quantile-quantile plot. So we take the quantiles of the data and we align those with the quantiles of a normal distribution. It uses this function QQ capital P plot in the CAR package. We put in the residuals, and there's a couple other options which are not very important actually to put in there. But we create this plot here, which gives us our residuals on the vertical axis, and along the horizontal axis is the normal quantiles. So if the residuals that we see are normal, then all these points would line perfectly on that blue line. And I will tell you that this plot looks amazingly good. You always get a few on either of the tails that sort of deviate a little bit from the blue line, but these are very well behaved. In the lecture notes, I talk about what happens when you get skewness and you get these sort of curved down or curved up situations, or you have kurtosis, which is sort of pointy or flat distributions where you get sort of an S shape. But this looks fantastic, and it should, because we saw up here, this looks like a normal distribution. So same answer here. Because the residuals follow the straight line here of the normal quantiles, it appears that the residuals are consistent with the model assumptions of normality. Okay, and that, something like that's a good thing to write here. Finally, we can use a formal test of normality to set up a hypothesis test. So here the null hypothesis is that the residual distribution is normal versus it is not normal. And we can perform a test. Now there's like 12 or more normality tests out there. And I tend to like the Anderson-Darling normality test. It puts a good weight of the sensitivity of the test out in the tails, where the tails are really what will affect the quality of the model fit and whether your conclusions, it will affect your conclusions the most. There are some other tests. I wonder if I think I took away. There's one called the Kolmogorov-Smirnov test, which is often used, but I think it puts too much weight near the middle, which is not where problems are. So you're unlikely to detect real problems with the Kolmogorov-Smirnov test. Anyway, I show two of them here. There's a Shapiro-Wilk test, which is just fine, and Anderson-Darling test, and then a Kramer-von Mises test. And each of these are shown in more detail in the lecture notes and discussed what model assumptions go into each of these tests. But what I will say is that if you use the Shapiro-Wilk test, maybe I'll say one more thing. Statisticians often do not use 0.05 as a cutoff for normality tests, but something more like 0.1. And that's because we don't really want to cut it close with model assumptions. If it seems like model assumptions are not going to be satisfied, we would prefer to look toward a non-parametric method that does not require these same model assumptions, so that we're conservative on our inference in our decisions. So let's see, what do we have here for our results? So if we're looking at 0.1, based on the Shapiro-Wilk, we would reject the null and conclude that our data are not normal. Based on the Anderson-Darling test, we have a 0.1, just over a 0.1, so we would fail to reject the null. That means we're consistent with the null, that the data appear normal, and Kramer-von Mises is larger also. And so I want you to interpret the conclusion of the Anderson-Darling test. And I think I've already said enough for you to be able to answer that well. All right, so those are the three ways of looking at the normality assumptions. In practice, do I do all three of those all the time? No, but I usually do in practice, in my own research, I will always use a QQ plot, and because this gives me some information about curvature, which if there's curvature here, that means there's something about skewness. I almost never use a formal hypothesis test for normality, because almost all the information that I need I can interpret from the QQ plot. Plotting the residuals like this doesn't hurt either, but I'll typically know what that plot looks like just by looking at the QQ plot. But that's more about experience. In the beginning of my career, I did always plot the residuals, because plotting the residuals and plotting the QQ plot and correlating those two in my mind allowed me to learn how to interpret the QQ plot. And these formal tests, like I said, this should be consistent with what you see in the QQ plot. Anyway, I would say there's no problem here with normality. All right, let's move on to equal variances. So we need also, in an analysis of variance, that the spread within each of these three groups are the same. And spread can be measured by variance, or the square root of variance is the standard deviation. Now, why do you think the zero cigarettes group appears to have so much more spread than the smoking groups? Now, it's not because the variance is different. In fact, look at the box plot width. See how the height on the zero group is basically the same as for the other two smoking groups? It's not the variance that's different, it's the sample size. Because there's more than twice as many non-smokers as there are in either of the smoking groups, you have more opportunity to see unusual observations, these high values and these low values of birth weight. And so the more babies you see, the more of the big and the small you're likely to see. Now, you also see a lot more in the middle. That's why you see all the dark points, where there's lots of points that are overlapping here. But you also see the extremes. This is why countries with large populations do really well at the Olympics. It's all that plus the wealth of the nation, those two things. But it's when you have lots of people, you are going to see fantastic athletes because you've got so many more people to select from. If you're a tiny country like the Netherlands, it's unlikely to produce a superhero type athlete, and when you have such a small group. All right, here we are. Okay, equal variances. All right, so let's start by looking at the numerical summaries. I am starting with the data set. I'm grouping by the smoking groups, and within each smoking group, I'm calculating the mean, standard deviation, and the sample size, and plotting that table. And here's what we've got. We've got the table. These are our three smoking groups. The means, 7.7, 7.2, 7.2. Standard deviations, basically 1.0, all of them. Sample sizes, like I said, the sample size for the non-smoking group is quite a bit larger than the other two. But these standard deviations are basically all the same. So looks like this assumption is going to be met as well. So go ahead and basically write that interpretation here. There are also formal tests for equal variances, and we can set it up just like we did for the ANOVA for the means, but instead we're doing a hypothesis test on the variances. Are all the variances equal, or is at least one pair of variances different? And we can, I think I show 3 versions here, yeah. And each of these have different model assumptions. The first is that if the populations are normal, then this is the best test to use. So we use Bartlett's test, and we get a p-value of 0.8. That's very large, of course. And is the p-value less than 0.05? No. Therefore, we fail to reject the null and conclude that the variances are equal. If we didn't have normality, recall, like we tested normality above and we concluded normality seems appropriate. So this is the best test to use, and you would stop here. Now, if you didn't have normality, then Levine's test would be a good choice. And again, we have a p-value greater than 0.05. And we also have a non-parametric test, which doesn't make any model assumptions, and it also says that variances look equal. So go ahead and interpret the results. I've said enough for you to write an answer here. Okay, I say also if normality was reasonable, then use Bartlett's, otherwise use Levine's. All right, we are almost at the end of here. If the ANOVA hypothesis was rejected, so let me page up for a moment. We did the ANOVA, and we had a p-value that was small. So we rejected the null in favor of the alternative. So yes, we rejected the null. Then perform follow-up post hoc pairwise comparison tests. I'll say, let me pause and say this. In your project, you may test a hypothesis and fail to reject the null, basically concluding that the means are equal across your groups. If that's true, then you're done. Stop. You don't go on to do pairwise comparisons. And you can just say that, like, I didn't go on to do pairwise comparisons because I didn't reject the null hypothesis. All the means are equal. Okay? All right. But in this case, yes, we do perform these post hoc. Post hoc means after, right, afterwards. Pairwise comparison tests to determine which pairs of means are different. And there are several multiple comparison methods that I describe in the notes. There's Fisher's least significant difference, which you should never use. There's Tukey's honest significant difference, which seems like a jab at Fisher, honestly. There's which is typically a good one to use. There's Bonferroni, which is typically too conservative, and then there's like a dozen more that people have developed based on your scenario. I would say that if you don't quite know what to use, Tukey's, very few people are going to argue that Tukey's would be appropriate. There are also special cases, like there are cases where you don't care about every pair compared to, or every pair of comparisons that, you know, we don't care about, say, the two smoking groups being different. We only care whether smoking is different from non-smoking, that sort of thing. If you were doing a clinical trial, you might only care about whether treatment A, treatment B, treatment C, if any of those was different than the placebo group, but you don't care whether the treatments are different from each other. There are methods for those type of single comparisons. There's also comparisons about order, like if your categories are ordered like ours is, about like 0 smoking, less than a pack, more than a pack, you might be testing consecutive pairs and not the first and the last one against each other. So anyway, just saying that there are scenarios, there are pairwise comparison methods out there for specialized scenarios. All right. This is the first year. I don't think this is in the lecture notes because this is a fairly new package, and I love this package. The estimated marginal means package by Russell Length. He's an alumni from the University of New Mexico about 40-something years ago, and a famous statistician who's done fantastic work over his career. And he's written a couple great packages. And he had this old package, LS means, but he's improved it with this estimated marginal means package. And that's what we're going to use here. Go ahead and read all this stuff. All right. Let's perform some pairwise comparisons. I've got some extra code here. Not really extra, but I've built in some stuff in case you wanted to play with it. Let's first just look at this. Now, in the EM means package, I'm going to run EM means, and I'm going to give it the ANOVA object that we fit earlier. And the specifications are we want to compare the groups by the smoke categories. And if we put that result into EMM cont, CONT is for contrast, and look at those, print out those contrasts, then we get, for each of the smoking groups, we get the means, and these are the same means that we saw before. We have the standard error of the means, the degrees of freedom, and then confidence intervals for those means. And these should basically be, these will be similar confidence intervals, but they'll be a little bit different. Is that true? They might be the same confidence limits that we provided in our own plot at the top. Confidence level used was 95%. Okay. Next, let's do the pairwise comparisons. So if we take that result that we just created and ask it to produce pairwise comparisons and choose an adjustment method, so adjust equals, and that's what I put up here. I created an adjust method vector. So I create this vector here, and notice I'm selecting index 2. The second index is Tukey. So that is the adjustment that we're performing. This allows me to just change this to 3 or change it to 1 and therefore get the Bonferroni or the unadjusted comparisons. But right now we've got Tukey comparisons right there, and we print those out. And this is where our inference is going to be for the differences. I've got the contrasts, and so I've got 0 versus or minus the less than 1 pack of cigarettes group. The estimate is 0.5. That is children or infants who are born from the non-smoking group are half a pound heavier than in the low smoking group. For that estimate, we have a standard error and a degrees of freedom, and the t statistic is the estimate divided by the standard error, and we compare that t statistic to a t distribution with 677 degrees of freedom, which is basically a normal distribution, because the t distribution in the limit as the degrees of freedom approaches infinity converges to a normal distribution. That is very far out on the tail, 5 standard errors out. Usually, right, 2 standard errors gives us a p-value roughly 0.05. So this is very far out there. And so our p-values very, very small. So this is strong evidence that the 0 group is different than the low smoking group. Let's take a look at the second one, 0 group versus the pack or more a day. The estimate is 0.46, and again our p-value is very, very small. So there's evidence that the non-smoking group is different from the high smoking group. Finally, what about the 2 smoking groups? So now we have the low smoking minus the high smoking. We have a negative 0.04, that's close to 0, and the p-value is large, 0.9. So there is not evidence that these 2 groups differ. And that is consistent with our plot at the very beginning. It may surprise you that, in fact, the birth weights for the low smoking group are a little bit lower than for the high smoking group, because I would think that there would be an additive effect, that as you smoke more and more, that probably contributes to lower birth weights. But I would also say that this is a very small effect, and we may not have evidence enough, a large enough sample size to really detect what that difference is once you get beyond 20 cigarettes. Okay, there is also a comment here that there's a p-value adjustment, that the Tukey method is for comparing a family of 3 estimates. So we have adjusted these 3 p-values. We've made each of the p-values a little bit bigger so that we can still compare it to 0.05, and have adjusted it relative to the Tukey method. All right, finally, we can also create a plot. And I really, really like this plot. We put in the EMM cont, that's what we created initially, that contrasts. And we're going to say comparisons equals true. I think that puts in the red arrows. The adjustment method is the Tukey method. And so this is another handy reason why I should create a variable like this, because I used it both in the pairs function and in the plot function. So if you change it one place up here, then it changes it for all of your inference. You can't accidentally forget to change it everywhere. You could make the plot horizontal, and I've created a label on the y-axis, which is actually the x-axis. Anyway, that's how it works. And let me describe, oh, this plot, I think, let me scroll up for a second. Yes, okay, so I've got comments here about how to interpret the plot. I'm going to just discuss it, but please read that short paragraph. It is common for non-statisticians to use confidence intervals, which are the blue bars, to determine whether or not means are different or not. And that is entirely inappropriate. Instead, what this plot does, it also creates these red arrows, which I've never seen anywhere else except from in this package, which does allow you to determine whether or not two means differ. And if red arrows overlap by drawing a horizontal line, if they overlap, then they're not statistically different. And if they do not overlap, then they are statistically different. So the three pieces of information that are on this plot are the black dots are the means, the blue bars are 95% confidence intervals, and the red arrows are used to determine if pairs of means differ by drawing horizontal lines and seeing if the red arrows overlap. And so from here we get that the zero cigarette group doesn't overlap with either of the smoking groups, so it is different from the other two, whereas the two smoking groups, the red arrows overlap, therefore they are not different. Okay. And so I have set up a piece of text here, and I would like you to say whether or not pairs of means are different. And we've looked at a few sources of evidence for that. I think that will be straightforward for you. Finally, because it is sometimes handy to have a very short visualization that you can do in text for whether pairs of means differ, I have this last piece of code, and this is something I also discuss in lecture notes. Summarize the results by ordering the means from smallest to largest, typically, and grouping pairs that do not differ by connecting them with horizontal lines. Okay, so I will do this with you. I'm going to go to the very bottom, and I'll keep that stuff there and just sort of put our own stuff over here. So we've got, let me go find the table that had the means in it. I'm paging up. Here we go. Okay, this piece of code has the numerical summaries. I'm going to copy this table and put it in the code with us to work from. Okay. So the means, the smallest mean is this group here. So I'm going to, you know what, I'm going to do two things. I'm going to sort of label this table group and mean. Okay, then the second smallest mean is the 20 plus cigarette group. Boy, I sure am clumsy when I'm not on my usual text editor. And then 0 cigarettes. Those don't look like they're quite equally spaced. Okay. So now, which groups, the instructions are, replace this example with your results. These groups are ordered by mean, so A is the lowest mean and C is the highest. And then you draw lines to connect groups that are not different. Okay, so in this example, I've got A and C differ because there's no single line that connects both A and C, but B is not different from either, right? So A and B are not statistically different, and C and B are not statistically different. Now this may seem like a contradiction logically, but in statistics this type of conclusion is just fine, right? So A and B might have means that are a little bit different from each other, but not so different to say that we have enough evidence to say that they're actually different. Similarly, B and C might have means that are a little bit different, but not enough to say that they're different. But if you sort of add the difference between A and B plus the difference between B and C, now it looks A and C are different enough to say, yes, those two are different. So it's really about how much evidence you have. So let's take a look at our case. We decided that 19 SIGs and 20 SIGs were not different from each other. And if you wanted to, you could draw a line just for 0 SIGs, because that was a group all on its own. It was different from the other two. And so I think that's a fine summary of the results. If I was in your position, I would follow these instructions to say, replace this example with your results. I would delete that. If you did what I did and you copied this table down, you could just leave it there. It's a nice summary, or you can remove it. It's up to you. But this, in fact, and you don't need the mean line in there either. It's enough to do that. But I would keep the mean in there. What the heck? It gives you some helpful information. And that is the end of the assignment. So I hope that was an informative walkthrough on the analysis of variance assignment, and I hope you all do very well.